Hello physicists! Today we are going to be looking at all of the capacitor section on the A Level Physics specification. Well, let's get started. First of all, the symbol for a capacitor is as follows. It is two parallel lines. Now let's imagine that we put a capacitor in a little circuit in which we have a cell. This capacitor here is going to start charging. The idea of a capacitor is to store electrical charge. The amount of charge that is stored on the capacitor will be proportional to the potential difference V across the capacitor and across the power supply that is charging it. The constant of proportionality between them is known as the capacitance, and it is given the symbol C. Rearranging for C, we get that C is equal to Q divided by V, and this leads us to our definition of capacitance, that capacitance is the amount of charge stored per unit of potential difference. The unit for capacitance is known as the farad. 1 farad is defined as the amount of capacitance we would get when we have 1 coulomb of charge that has been stored for 1 volt. We can explain the charging of a capacitor in terms of electron flow. First off, in a cell, during the charging of a capacitor, we're going to just connect this cell to a capacitor, as we can see over here. The electrons are going to flow from the negative terminal of the cell to the negative plate of the capacitor. There's going to be some excess electrons that are going to gather on the negative plate, and those are going to repel some electrons of the positive plate of the capacitor, which are going to move towards the positive terminal of the cell. Overall, the plates are going to acquire an equal and opposite charge. On the other hand, we can also use a capacitor essentially as a source of power in a circuit. For instance, we can take a charged capacitor and we can connect it to a light bulb. When we connect the capacitor to this circuit, the excess electrons are going to flow from the negative plate. In this case, this will be clockwise to the positive plate, and the charge on the capacitor is going to be decreasing. Let's go over adding capacitors in series and parallel. We're going to start off with adding capacitors in parallel first. So if we have capacitors in parallel, for instance, here we have two capacitors of 300 microfarads which have been connected in parallel. You can see the junctions over here. In parallel, the total capacitance, I'm going to call that C total. C total is equal to just the algebraic sum of the two numbers. So that would be, let's say, C1 plus C2. Applied to this problem above, the total capacitance is going to simply be equal to 300 plus 300 microfarads. So let's write that 300 plus 300, which will be equal to 600 microfarads. If the two capacitors are connected in series, the rule is as follows. 1 over the total capacitance C total will be equal to 1 over C1 plus 1 over C2. It is best to input this into a calculator by just finding the C total as brackets 1 over C1 plus 1 over C2, then raise this whole expression to a power of -1. For instance, the total capacitance in this case will be equal to 1 over 300 plus 1 over 300, raise this whole expression to a power of -1, which is going to give us 150 microfarads. If you're wondering how to derive those two rules or why they're exactly the opposite to adding resistors, check out my video in the playlist of my full online lessons on capacitors, which is in the description. Here are a couple of more commonly misunderstood facts about capacitors in a series and in a parallel circuit. Let's start off with a parallel circuit. First off, because this is a parallel circuit, the voltage or the potential difference is exactly the same across all the different parallel branches. So the potential difference of our source of EMF, in this case this is a cell, is going to be the same as the potential difference over the first capacitor when fully charged and the potential difference over the second capacitor when fully charged. However, because the current is actually shared in a parallel circuit, is being added up, this also means that the charge is going to be shared as well. In practice, this means that the total charge Q total will be equal to Q1 plus Q2. I mean, if we wanted to, we could also write that C total, the total capacitance, times the potential difference will be equal to C1 times V1 plus C2 times V2. However, because the potential difference is exactly the same, the voltage will be also exactly the same, and this is why we can also see that the rule for capacitance is that C total is C1 plus C2, because all of the potential difference is going to be cancelled out. In a series circuit, each capacitor is going to experience the same current, so this means that it will acquire the same amount of charge, and this is really important because it's really counterintuitive. This will also be the total amount of charge within the circuit. So Q total will actually be equal to Q1, which will actually be equal to Q2. The PD is shared by Kirchhoff's second law, and which says that the sum of the EMF, so let's call that V total, will be equal to V1 plus V2. Let's have a look at a capacitor discharging. For instance, we have this capacitor here that is connected across a resistor. We're measuring the voltage across this resistor, and if we did that, we are going to see that it will be decreasing exponentially. The equation for the voltage across a capacitor at a time t after it begins to discharge is that V is equal to V naught e to the minus t over CR, where V naught is the initial voltage, T is the time of interest, C is the capacitance, and R is the value of this resistor. Because Q is equal to CV and C is constant, this equation also applies for the charge. So Q is equal to Q naught e to the minus T over CR. Additionally, it will also apply for the current, which will also be decreasing exponentially. Applied this equation to a little problem over here. We have a 500 microfarad capacitor which is charged up to 6 volts, which is going to be our initial voltage. It is then discharged for a 500 kilo ohm resistor. The value of the resistance is quite large, so I'm expecting the voltage to still be relatively high, and find the PD across the capacitor 150 seconds after it begins to discharge. Okay, well, let's write down my equation over here. So I'm going to say that V is equal to V naught e to the minus T divided by CR. My initial voltage V naught is 6.0 volts. I'm going to multiply this by the exponential of minus T, which is 150 seconds. I'm going to divide this by CR, which is 500 microfarads, so that's times 10 to the power of minus 6 farads, times my resistance, which is 500 kilo ohms, so that's 500 times 10 to the power of 3. When we carefully input this into a scientific calculator, we're going to get 3.29 volts at time is equal to being equal to 150 seconds after the beginning of the discharge. Now let's have a look at what actually makes a function an exponential function. We need to know the constant property ratio of exponential. In equal time intervals, the initial voltage over another one, let's call it V1, is going to be equal to V1 divided by V2 is going to be equal to V2 divided by V3. In practice, this means that in equal time intervals, the exponential function will be decreasing by the same factor. For instance, let's say that the value decreases by a factor of a third from V1 to V2. This would also indicate that the function will also decrease by another third from V2 to V3. This is the nature of the exponential decay. Talking about exponential functions, let's also remember how to rearrange this equation, let's say for the amount of time t. So I'm just going to write over here for practice, we can rearrange for t. The first thing that we're going to do will be to just rearrange for the exponential. So v over v naught will be equal to e to the minus t over cr. Then I'm going to take the natural log of both sides of this equation. So I'm going to get that ln of v over v naught is equal to the ln of e to the minus t over cr. Now remember, the natural log and the exponential functions are inverse functions, which means that essentially they undo each other. So this would mean that ln of v over v naught, well, that's not v, okay, there we go, v over v naught will be equal to minus t over cr. Then what I'm going to do is I'm going to multiply both functions by the power of minus 1. So what I'm going to get is that minus ln of v over v naught is equal to t over cr. The minus sign is actually going to flip the natural log. So this would mean that this will be ln of v naught over v, which is equal to t over cr. And finally, all I need to do is just rearrange for the time. I'm going to get that t is equal to cr multiplied by the natural log of v naught over v. Let's revise this property known as the time constant next. The charging and the discharging of a capacitor depends only on the resistance and the capacitance. So we define this quantity, which is normally given the Greek letter tau, as capacitance times resistance. This is actually a time. Let's show that it has the units of time. So I'm just going to multiply the two quantities. So C times R is going to equal, now because Q is equal to, just going to write this on the side, Q is equal to CV, so this means that capacitance is Q over V. So I'm going to put that in there. This will be Q over V times resistance, which is just V over I, like so. Those guys are going to cancel out, which means that I'm left with Q over I. But remember, Q is equal to I times T, which means that time is equal to Q over I. So this quantity, C times R, actually has units of time. So this time constant T is going to have the units of time, which are seconds. What happens at time is equal to the time constant? This seems to be a special time. So in fact, let's calculate the PD at time is equal to the time constant. So I'm just going to write down my exponential equation. V is equal to V naught e to the minus t over CR. However, rather than just time, I'm going to write the time constant. Well, let's see what happens. V is equal to V naught e to the minus, now the time constant is just CR, so what I'm going to get is CR divided by CR, and as we can see, no pun intended, those two guys are going to cancel out, which will lead us to the fact that V is V naught e to a power of minus 1. Now, e to the power of -1, we could just put this into a calculator, and what we're going to get is that V will be 0.37 up to 2 significant figures times the original voltage V0. And in fact, this is the very definition of the time constant, that at time equal to a time constant, the PD will drop to 37% of its original value, so will the charge, and so will the current. We can often figure out the time constant directly from a graph. This is quite an obvious example, but the principles of it can be applied to most graphs of potential difference or current or charge against time. For instance, we have the exponential decrease in PD in a circuit in which a capacitor is discharging for a 5 kilo ohm resistor. We can use this graph to figure out the capacitance of the capacitor. First off, if we have this graph, we have the time constant, because the voltage is initially 100, then drops down to 37 volts, which is 37% of its initial value, in 25 seconds. This would mean that the time constant T is equal to 25 seconds. However, remember that the time constant is the product of the capacitance times the resistance, which would mean that our capacitance will be equal to our time constant divided by the resistance, which will be 25 divided by 5 kilo ohm resistor. It's going to be 5 times 10 to the power of 3. And if we put that into a calculator, this will, well, just give us 5 times 10 to a power of -3 farads. Finally, let's have a look at the charging of a capacitor. In order to do so, let's imagine a circuit of EMF V0 that we've connected to a resistor R and a capacitor which is initially not charged. As soon as this circuit is connected, this capacitor will start charging. Now, as the capacitor starts charging, the voltage across the capacitor will increase, so this guy over here will start increasing, and the voltage across the resistor will start decreasing exponentially. In fact, the PD across the resistor will be decreasing exponentially. So VR will be equal to V0 e to the power of -t over CR. You can kind of think of it as soon as this circuit is switched on, VR is equal to V0 and this guy is equal to 0, and then VC increases while VR decreases exponentially. We can use Kirchhoff's second law, that the sum of the EMFs. In this case, we only have one EMF, which is V0. The potential difference across the cell will be equal to VR plus VC, which is the voltage across the capacitor. And what we can do is just write down that V0 is, rather than VR, I'm going to write V0 e to the -t over CR plus VC. I can rearrange for the PD across the capacitor, and I'm going to get that VC will be equal to V0 minus V0 e to the -t over CR. We can take a factor of V0, and what we're going to get is that the potential difference across the charging capacitor will be equal to V0 1 minus e to the -t over CR, like so, which is a formula for the PD across this capacitor, like so. The formula for the PD across the resistor is given here. The same formula also applies for the charge across the capacitor, because Q is equal to CV. So what we can write over here is that Q across the capacitor will be equal to Q0 1 minus e to the minus t over CR. This will give us the charge across the capacitor at a time t. However, if we wanted to find the current in this circuit, notice that the current will be dropping down in this series circuit as the capacitor is charging. And this is because the PD across the resistor is going down. So what I'm going to say is that the current in the circuit will be decreasing as the capacitor is charging. And it will be decreasing by the same factor as the potential difference across the resistor. And in fact, in this circuit, I will be equal to the initial current, which will be the highest, e to the minus t over CR. When the capacitor has stopped charging and has reached the maximum potential difference, then the current will be dropped to 0. Okay, folks, well, this was the vast majority of the capacitor portion of the A-level physics specifications. Hopefully you have found this useful. If there are any questions, please leave a comment, and thank you very much for watching.